In this video, we will talk about Lorentz transformations in index notation, and in particular about the inverse transformation, which can cause some confusion. Let us start with the defining equation of a Lorentz transformation, which leaves the Minkowski metric invariant. If we contract this equation with the inverse metric, eta beta gamma, we can use it to raise this index of lambda here, and on the right-hand side, we get a Kronecker delta. We can then perform the sum over nu, which means we lower this index. What remains is an equation with the usual Lorentz transformation matrix lambda, another lambda with an unusual index position, and a Kronecker delta, which basically represents the identity matrix. So does this mean that the lambda with the unusual index position is the inverse? You might have noticed that we cannot simply interpret this as lambda times its inverse being equal to the identity matrix, since the mu indices are not next to each other. To fix this, we can transpose the second lambda such that now the index mu is next to each other, and we can interpret this as a matrix equation. But wait, this suggests that the transpose of lambda is equal to its inverse? This would be true for rotations, but a general Lorentz transformation consists of rotations and boosts. So what is going on? The solution is both equations are correct, but our interpretation of them is not. Let's talk about the first one first. The matrix lambda corresponds to the upper-lower index position, not to the lower-upper one. We have two options to deal with this equation. One is to simply define that the lower upper lambda is equal to the inverse Lorentz transformation with exchanged indices, such that the equation can really be seen as lambda inverse times lambda is 1. The other option is to pull indices up and down until we reach the natural index position of everyone that's involved. This would mean that a lower upper lambda must be written using two copies of the Minkowski metric, and a regular lambda in the middle. Now everyone has its natural index position. The only thing missing before we can write this as a matrix equation is that the index mu here and here is not right next to its paired index. By writing this first lambda as the transpose of lambda, we can now finally write this as a matrix equation. Since the inverse metric and the metric are the same matrix, we can drop the -1 here. We see that the inverse of the transposed lambda is eta lambda eta, and therefore the inverse of lambda is eta lambda t eta. Note that we use the natural index position for the transpose matrix as lower upper, which helps us to deal with the second equation from the beginning of this video. Here, the indices mu are paired up right next to each other, but the transpose matrix is not in its natural index position. Remember that lambda corresponds to upper-lower, and the transpose corresponds to lower-upper. So a transpose with upper-lower indices is not immediately clear. But same as before, we just have to use the metric to pull some indices until everyone has its natural index position. In summary, a transposed lambda with upper-lower indices should be written as the metric, a transposed lambda, and the metric, such that the equation looks like this. Since every index is paired up correctly and all symbols have their natural index position, we can write this as a matrix equation, where we see again that the inverse of lambda is equal to eta lambda t eta, and everything is consistent. In summary, here are all possible index positions of lambda and its transpose, together with which matrices they correspond to. And that's pretty much it for this video. Thanks for watching.